So that's when you know when you know sigma. But now we don't know sigma, right? We're in trouble. We don't know mu, but we don't know sigma either. But still, our goal remains the same. We try to figure out mu from x bar. Same goal, same goal. But now we're a little bit hobbled. We're like, oh, I don't have a tool that I used to have. Okay. So the beginning part of the story stays the same. The population, we have no idea. From there, we want to find the SDOM, right? Because we're going to figure out how good our sample is, right? We know the shape of our SDOM as long as our n is sufficiently big. But can we figure out sigma sub x bar anymore? No, we cannot, because we don't have this. We don't have sigma. So how can we figure out sigma sub x bar? We can't figure out that standard error. Here's where another idea comes in. There is another way we could estimate the standard error of the sampling distribution. That's going to be s, little s, sub x bar. Because here, we're going to use the sample's standard deviation, s, instead of sigma, right? And remember, s, it's more variable, not quite right? And because of that, we've corrected already a little bit by using n minus 1 instead of n, right? Already in s, right? But here, we're going to divide that by square root of n, right? So if you double-click on this, you would see the square root of the sum of squares divided by n minus 1, divided by the square root of n minus 1, right? And so you would see this inside of that, right, if you sort of double-clicked on it. So we've already tried to correct a little bit, but s is still really variable. It's not quite as good as having sigma. And so there are going to be other problems that we run into. So this is pretty good, though. And so it's a pretty good estimate, but you always have to keep in mind, okay, we have not quite a good, not as good of a standard error as we used to. So you're going to have to account for that. But the steps remain the same. So first, assume x bar for mu sub x bar, right? So put x bar here, right? 2, find z's for your capture rate, right? So if your capture rate is, for example, 95%, right? Then you would find the z-scores. And it's sort of helpful to memorize that for this capture rate, the z-scores are going to be plus or minus 1.96. It's going to come up a lot. So find the z-scores for your capture rate. But here we run into a problem. I wish we could use z-score. I really do. I really wish. But here's an issue. We actually can't, because s is too variable for us to assume perfect normality. And because of that, we can't use the z. And instead, we have to use, I'm going to erase here, we have to use the t, which is very, very similar to z. It's going to be very, very similar. Find the t-score for your capture rate. So instead of having, raw score, let me change the color. Instead of having raw score and z-score, instead we're going to find t-score. Now, for now, you just need to know that you could find your t-score in the back of the book, but in the next lesson, we're going to go over why you use t and why can't you use z, right? Because that's a big story. Okay, so you're going to have to find t. Once you find the t's for your capture rate, and that will also be plus or minus, t is going to be very similar to z-score. Then you're going to use this formula. You're going to use a very similar idea to the z-score confidence interval, where you want to know x bar plus or minus how, and t-score is also going to tell you how many standard errors away, t times standard error. But remember, you use t when you estimate this from sample. So if we unpack this, this is what it's going to look like. X bar plus or minus t times, this is that estimated standard error, s over square root of n. Right? So it's still the same idea. It's how many jumps away, figuring that out, and then multiplying that to the length of the jump, right? And adding that to x bar for the high value, and then subtracting that from the x bar for the low value. Now, in order to find t, here's what you need to know for now. You need to know whether it's a one or two-tailed distribution, right? So if your confidence interval is two-tailed, then remember these are 0.025, because you have to sort of split the remaining 5% on both sides, right? But sometimes for t-values, they'll only give you one-sided, right? So they might give you a one-sided 5% or one-sided 0.25%. So you have to just keep in mind whether it's one-tailed or two-tailed. And also, the t-distributions are a whole bunch of different distributions. There are a whole bunch of different tables, basically, right? So you have to also know, must know what's called the degrees of freedom. And for now, you could remember degrees of freedom as n minus 1. There are reasons for all of these things, why we use t, why we use degrees of freedom, all this stuff. And that will be covered in the next lesson. So for now, here's what you need to know. You need to know whether it's one-tailed or two-tailed. You also need to know degrees of freedom. Once you have that, you could actually look it up in a t table, usually found in the back of your book. It might also be called the student's t distribution, because a guy named Gossett invented it, but he was actually contracted to work for Guinness Brewery, and so because of that, he couldn't publish it under his actual name, so he published it under the pseudonym Student, and because of that, it's called the Student's T. And so you could look up your degrees of freedom, and then look for the area that you need, and then go down and find the t-score. Very similar to z-score. All right. So now let's go on to some examples. So example 1, consider two extreme situations. N equals 10, so sample size of 10, and n equals 1,000, a way bigger sample size, right? If you use S in the formula for CI, given sigma, so here's the actual formula for when you have sigma, right? So we use 1.96 because you use the z-score, right? Which of these situations would you expect to give a capture rate closer to 95%? Here's what this question is really asking. So when you know sigma, for confidence interval, you really need x bar plus or minus, so this is for 95% confidence interval, 1.96, so that's my z, right, times sigma over square root of n, right? But what it's asking you is, what if you substituted in s? What if you substituted in s? So here, we don't know sigma. So here, but we are going to just take this formula and use this z value. S over square root of n. Well, in order to answer this question, you really only need to keep in mind one thing. When is S more like sigma? S is more like sigma when n is very, very large. S is similar to sigma when S is, sorry, when sample size is large, right? So this situation would give you, even if you plugged in S here, that would give you a very, very close capture rate to 95%, right? These would be very, very similar. However, when n is 10, you have more uncertainty. And because of that, the t distribution, it's not as tight. It's actually more like spread out. And because of that, when n is equal to 10, you don't capture 95% just by being about 2 standard deviations out this way and this way. That won't capture 95% of those samples. In fact, you'd have to go out further to capture 95%. And so this is going to be much closer to 95% capture rate than this. This is going to give you a smaller capture rate. And that's because your S is going to be more variable, and because of that, your t distribution is going to be more dispersed, because more variable means sort of wider, right? Not as like tight.